So at the end of last time, we were doing this matching problem, de Montmort, and then I wanted to say a little bit more about that problem because it was a little rushed at the end of last time. So let's finish talking about that. That was an example of inclusion-exclusion. And then for the rest of today, I want to introduce independence. We've already kind of been talking informally about independence. We say things are independent. What does that really mean? Okay, and then the big main topic for this entire week is conditional probability and conditioning, so that'll be the rest of today. First, let me just quickly remind you of this de Montmort problem, matching problem. Continued from last time, just because I had to explain it a little too fast last time, and there were a couple more comments about this. This is sort of the most famous example of inclusion-exclusion. If you read the strategic practice and if you go to section, you'll be seeing lots more examples of inclusion-exclusion. But this is probably the most famous one, and it's a nice one. So I'm not going to write the whole thing again, but I'll just remind you of our notation from last time in case you forgot. It's hard to remember notation over the weekend, so I'll just remind you briefly. We have a deck of n cards. The cards are labeled 1 through n, and you're just playing this game where you're just flipping cards over one by one. You say 1, 2, 3, whatever. And you win if, in fact, at some point, the card that you name is the card that appears. Okay, that's the game. You want to know what's the probability that you win that game. Okay, so I defined AJ to be the event that the jth card matches. In other words, the jth card in the deck is labeled with the number j on it. And we were trying to find the probability of the union. And I want to explain this a slightly different way and then make a couple more comments about it. So what we're interested in is the union. And you can think about how to do this directly, but it's pretty hard. And inclusion-exclusion is the easiest way to do this. So if you remember your inclusion-exclusion, it says that this probability of the union is going to be something that looks like first you're going to add up the individual probabilities, then you're going to subtract the probabilities of different intersections, right? And then you're going to add triple intersections, and you're going to subtract and add, and you keep going like that. So in order to compute what we need for inclusion-exclusion, basically what we need is the probability of A1 intersect A2 intersect blah, 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 intersect AK. This is a handy trick. This is like really, really simple, and yet students for some reason don't like doing this. I highly recommend. What did I do here? I picked the first k of them for concreteness. What makes this problem doable, without spending weeks on it, is the symmetry of the problem. So I could have written, A7 and A9 and whatever subset of k of them I wanted, okay? But for concreteness, I'm just picking the first k. By symmetry, it wouldn't change. We could start introducing some if we wanted to be really formal, though, we could start writing like A sub j sub 1, A sub j sub 2, and you get all these double subscripts, and then people start to get confused. But by symmetry, it's the same as just writing this one down, okay? So it really helps to make it concrete. Now, this is just n minus k factorial over n factorial. That's immediate from the naive definition of probability, because we're assuming that all orders of the deck of cards are equally likely. That's the denominator. And the numerator, what this says is that the first card 1 is labeled 1, card 2 is labeled 2, blah, blah, blah. Card k is labeled k, okay? So that means the rest of the n minus k cards could be in any order, but the first k are constrained. So that's immediate from the naive definition. So that's what we did last time. And then I'm going to explain it in a slightly different way now. Just notice that there are, how many of these terms are there? Well, if you look back at your inclusion-exclusion, we don't just do this for 1 through k, obviously. We do this for all subsets of size k. So we're going to have n choose k terms that look like this. And n choose k, remember, is n factorial over n minus k factorial k factorial. Such terms, and they're all the same by symmetry. So symmetry is the key to this problem, plus inclusion, exclusion. And now that this makes it easier to see than what I wrote last time, easier to see why it's going to cancel into something very nice. Because we have n minus k factorial over n factorial. We have n factorial over n minus k factorial. It cancels. The only thing that's left is the 1 over k factorial. So now by inclusion, exclusion, it's immediate that the probability of the union equals 1 minus 1 over 2 factorial plus 1 over 3 factorial minus dot, 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 plus negative 1. And then if you look at the last term of inclusion, exclusion had a negative 1 to the n plus 1. And I think I forgot the plus 1 last time because I was writing it in a hurry at the end of class, so you may want to fix your note. There was a plus 1 there. That's the last term. And let's just do a quick sanity check. Does this 1 over n factorial make sense? Well, this 1 over n factorial term is saying the cards are perfectly ordered 1 through n, right? This is the case where all of them match. Well, there's only one way that could happen, that the cards are 1 through n. So this term should make sense. Okay? So that's what we did. And then suppose we wanted the probability. Often the problem is phrased the other way, as what's the probability that there are no matches. So of course that's just going to be 1 minus this. No match equals, and just for practice, let's write that in set theory notation. Remember from your math review, if you take the complement of a union, it's the intersection of the complements, right? So the complement of that is the intersection of AJ complement, and that's just 1 minus this. So I'm just going to write 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus dot, 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 plus, now it's negative 1 to the n because the sign flipped. All right, so this is the exact answer for the probability of no match. Now, this thing looks pretty complicated, so what if we wanted an approximate answer? Then you have to recognize the pattern here. Whenever you see something that looks like, factorials in the bottom, that should be making you think of various Taylor series, right? And the two Taylor series that we need over and over again in this class are the geometric series and the Taylor series for e to the x. So when you see something like this should immediately remind you of the Taylor series for e to the x. Of course, we could put a 1 factorial here and a 0 factorial there without changing anything. That's exactly the Taylor series for e to the x evaluated at x equals minus 1. So this is approximately 1 over e, which is about 0.37. And most people find this result pretty surprising because, first of all, where did the e come from? Seems like you have a pretty discrete, e is making you think of logarithms and maybe some calculus, continuous stuff. This just seems like a discrete problem, just like, arranging these cards randomly. What does a deck of cards have to do with the number e? The other thing that's surprising about it, well, actually, I haven't done a survey of this, not like formally. It would be interesting to see what people's intuition is if you let n goes to infinity. I'm pretty sure most people who hadn't seen this would guess that the probability of no match either goes to 0 or goes to 1, right? And it sort of depends whether you're a pessimist or an optimist, right? Because you have this, if n is getting very large, you have like, 1 billion cards, okay? Now, each one of those cards is extremely unlikely to be in its position, but you have so many chances. So who's winning kind of that competition between the fact that it's so unlikely for each one, but you have so many of them? Somehow those two kind of competing forces reduce to 1 over e. And we're going to see the number 1 over e a lot in this class. Sometimes I like to say that if you have no idea whatsoever, on a problem and you had to guess, you should guess 1 over e. You don't have a good chance of getting it right, and you're supposed to justify your answer, but probably 1 over e is going to give you a better chance than anything else. So, so this is exact as n goes to infinity. It will converge to 1 over e. But even if n is like 10 factorial is over 3 million. It's a huge number. So even if n is 10, I think that this number is correct to within like something like 2 out of 100 million accuracy, something like order of 10 to the minus eighth, the difference between this and this if n is 10. So it converges to 1 over e extremely fast. Okay, so that's just an illustration. I like this problem because, well, it's kind of cute. It illustrates 1 over e. It illustrates inclusion, exclusion, it illustrates symmetry, and those are all things we're going to see a lot of. So, okay, so that's that problem. So now I said we'd define independence, and it's very easy to define. It's not so easy to understand fully the definition. So the definition is very, very simple. So we already have some intuition about what does it mean to have independent events. That is like one of them gives you no information about the other one, basically. But that definition isn't, is too vague to actually verify, are these events independent or not. So if we have two events, A and B, we say that they're independent. We're assuming that we have a sample space and a probability function P that we're working with. So it's within the context of one experiment and one probability P that satisfies the axioms we've been talking about. Okay, they're independent if, and the definition is just that the probability of A intersect B equals P of A, P of B. So that's pretty intuitive. It just says, what's the probability that both A and B occur? Well, the probability that A occurs times the probability that B occurs. They have nothing to do with each other, independent, so we just multiply. That's the definition. We'll see some equivalent forms of it later. Oh, this board is very noisy. I want to contrast this with disjoint, because that's a common mistake, and that's a terrible, disastrous blunder. This is completely different from disjointness. If I say that A and B are disjoint, that means that if A occurred, then B cannot possibly occur, right? That's opposite to independence. Independence says if we know that A occurs, it tells us nothing whatsoever about whether B occurs. Disjointness says if A occurred, then B can't occur. So they're completely different concepts, but for some reason they get confused a lot, so that's why I was mentioning that. That's for two events. Let's just define what happens with more than two. If we have events A, B, C, this is the definition of what does it mean for three events to be independent. Well, first of all, we want any two of them to be independent. It would be kind of weird to say that all three are independent, but A and B are not independent. So we have P of A, B. And by the way, sometimes it's fun to write commas instead of intersections. And that doesn't cause any problems unless we start bringing in unions and things like that. So sometimes I'll write probability of A and, because I'm interpreting intersection as and. So sometimes I'll just write it as a comma. Mathematically, this means the intersection, but intuitively, it means what's the probability that both A and B occur. Okay? So we want, this says A and B are independent, and of course we want A and C to be independent. And of course we want B and C to be independent. And then the question is that enough? If we just had these equations, we'd say that's pairwise independent. That is, we have three events, and if we take any two of them, they're independent. And the question is whether that's enough. And the answer is no. We also need one more equation, P of A, B, C equals P of A, P of B, P of C. So the kind of a slogan that some people sometimes say is independence means multiply. That's a little too vague, though, right? Because it depends what you're doing. But if you have independent events and you want the probability of all of them happening, then you just multiply. Okay, so clearly we want this to be true. Now there's a question of, do these pairwise ones imply this one? And the answer is that it doesn't in general. There are some examples of things like this in the strategic practice, and I would suggest that first, I think it's just good practice with the definitions to try to construct your own counterexample, and if you get stuck, you can look at the solution in the strategic practice too. And I might come back to this later, but it would be better to think about it first, and I want to get to conditioning. But in general, we can't get rid of any of these conditions. And you also can't say that this one will imply these ones. We just need pairwise independence, and we need all three of them at once. Okay? So that's just the definition. Similarly, for events A1 up to AN. So if we have n events, I'm not going to write down all the equations because it's completely analogous. Once you understand the case with 3 of them, you could do n of them. Okay, but we would say, well, first of all, any 2 of these have to be independent, and any 3 of them have to be independent, and any 4 of them. So no matter how many of them you take, and you do something like this, it's just the product. So that looks pretty unwieldy. We have lots of different equations. So later we'll see other ways to think about independence. But just the basic rule is independent means multiply when we're trying to find the probability of an intersection. So that should be true no matter how many of the events we take. We could take any subset of these. Yes? What's the other way? So the question is whether this holds the other way too. Yeah, we're using multiple. I mean, this is just kind of a slogan. This is not a math statement, but this slogan is just a paraphrasing the definition. It's saying if all of these multiplication rules hold, that's the definition of independence. So it's true both ways. Okay. So we'll see other ways to think about independence later, but for now that's just the definition. And hopefully it makes some sense. You can also think about the naive definition and think about the naive definition of probability and your naive intuition of independence. Put those together and see whether it's consistent with this, and I think it will be. But if not, let me know. But just for now, that's the definition, but I think you should think about it. Okay, so I want to do one example. One more famous example. And then we'll do conditional probability. Okay, so this is another famous problem. I think it's from 1693, very old problem. This is called the Newton-Pepys problem. I think it's from 1693. Pepys was Samuel Pepys was this famous diarist who you might have heard about in a history course. Well, anyway, he wanted to know the answer to a problem involving gambling, involving dice. I wrote down some numbers here. He wanted to know the answer, and he couldn't solve it. So he wrote to Isaac Newton, and Newton solved the problem for him. So I wanted to talk a little bit about that problem. So here's the problem. We have fair dice, just usual 6-sided dice. So the sides are numbered 1 through 6, all equally likely. And the question is, which of these is most likely of these 3 possibilities? Okay, the first possibility, let's call this event A. A is the event of getting at least 1 6 with 6 dice. So you roll 6 dice, and the question is, will at least one of the 6 dice have a 6 on it? So at least 1 6 with 6 dice. That's the first possibility. The second possibility is at least 2 6s. I won't write the at least again. At least 2 6s with 12 dice. Okay. And the third possibility, you might guess, is at least 3 6s with 18 dice. So you roll 18 dice, and you want to know, are there at least 3 6s? Okay, this question. So in 1693, this was a hard problem, and he, this guy wanted to know the answer, so he wrote to Newton, and he had a strong Pepys had a strong belief about which one of these was the most likely, but he didn't know any of the math to be able to back that up. And I'm curious what your intuition is. If you had to guess A, B, or C, which is the most likely, how many of you would guess A? Okay. How many of you would guess B? Okay. How many of you would guess C? All right. So I think C, definitely B did not win, so I think C beats out A, according to that informal poll. Now, C is what Pepys strongly believed, and he was asking Newton, is that correct? Can we back that up? And the answer is A. Now, it's not at all obvious, though. Okay, that's why he had to write to Newton. And what actually happened is Newton wrote back a letter deriving it and showing that A was the largest. And apparently Pepys had some other bet based on this that he reneged on because when he found out that he was wrong. All right, so now let's solve the problem. So let's just find. At this point, this should be a pretty easy calculation for us. So it shouldn't take too long. Let's find the probability of A. Well, this is similar to other problems we've done. You can use the naive definition because all 6 outcomes are equally likely. But let's do it using independence instead. Implicitly, I'm assuming that the rolls of the dice are independent. Either you roll, like in this case, either you roll 1 die 6 times independently, or you have 6 independent dice. So we're assuming we don't have like some weird situation where you have 6 dice that are kind of magnetically joined together so that they're all going to land the same way. So the 6 dice are independent of each other intuitively, but that intuition corresponds to that definition there. Okay, so I'm going to use independence. You could also use the naive definition, and you'll get the same thing. Now, as far as our strategy, when we see probability of at least 1, whenever you see at least 1, that should make you think of a union. Okay? Now, and when you see a union, one approach is inclusion-exclusion, but like I said last time, I try to find simpler ways when possible. So the first thing I think when I see at least 1 is it's a union, but if I do the complement, it'll be the intersection. And in this case, we're taking an intersection of independent stuff, so that means we just multiply. So that's going to be the most straightforward way to do it. So I'm going to do 1 minus, because I'm doing the complement. It's 1 minus the probability that all of the dice are non-6s. Right? Now, for each individual die, there's a 5/6 chance that it's not a 6. Independence says we can just multiply those, so it's 1 minus 5/6 to the 6, which agrees with what we would get from the naive definition, because in the naive definition, we would say there's 6 to the 6 possible outcomes, and each die has 5 possibilities if we're excluding 6s. Okay? So that should be basically immediate. And now let's do P of B. Oh, by the way, I computed the number, and it's 0.665. So it's about a 2/3 chance of having at least 1 6 if you roll 6 dice, which might not be what most people would guess if they had to guess what this probability is. But that's an easy calculation. Okay, now let's do P of B. Again, at least 2 6s. That means that the number of 6s could be anything from 2 to 12. Well, that seems a little unwieldy, so let's do the complement. So we're going to do 1 minus. So we're going to do 1 minus the probability of no 6s, and then minus the probability of exactly 1 6, right? That's going to be easier. So to do no 6s is very easy. That's just 5/6 to the 12th. That's just saying all the dice are non-6s. Minus the probability of exactly 1. And here we have to think a little bit more, but hopefully not too much more. We want exactly 1 6 and exactly 11 non-6s. So let's think of a specific way to do that. A specific way would be, suppose that we labeled the dice 1 through 12. Okay? So one way to have 1 6 would be if die number 1 has a 6, and the other 11 dice are non-6s. But that was just one possibility. Okay? The 6 could have been any of the 12 dice, so we just have to multiply this by 12. And this works out, if you compute this with a calculator, this is 0.619. So this is a bit less likely, 5% less likely. Lastly, let's do P of C. Again, I'm going to do 1 minus. And this time, just to save some writing, I'm going to write this as a sum. So I'm going to subtract off the possibilities where there are exactly two. Subtract out the possibilities where there are 0, exactly 1, or exactly 2 sixes, okay? So we're just going to subtract off those cases. So I'm thinking of, so now here I want to know if I have 18 dice, what's the probability that exactly k of them are sixes? So if we draw a little picture, we're going to number the dice 1 through 18. So I won't draw all 18 of them. Here's the first two and the 18th. It's pretty easy to draw dice, just draw squares. Now, one possible case, for example, if k is 2, and I want the probability of exactly 2 sixes, one possibility would be to have sixes here and here, and everywhere else is, I don't know how to write like non-6, but everywhere else other than these two is not a 6. That would be one way, right? But it didn't have to be die number 1 and die number 2. It could have been any of the 18 choose 2, right? So choose any 2 positions to put the 6s, and then put the non-6s everywhere else. That's what we're doing. Therefore, we can then immediately write down this is just going to be 18 choose k. We know, we're very familiar with 18 choose k by now, right? It's the number of ways to choose where the 6s are. And then for the 6s, it's 1 6 to the k. And then for the non-6s, it's 5 6 to the 18th minus k. This thing that I just wrote down is called a binomial probability, and we're going to be seeing a lot of these later. And I know some of you have seen binomials before, but it doesn't matter at all whether you've seen the binomial before in this class. What matters is that you understand where this comes from, not that you memorized it. And so whether you've seen the binomial or not, this should be something that, just from understanding the concept, this should be something that you can just write down fairly easily without memorizing it. Okay, but we are going to see expressions that look like this a lot in this class, so that's, just introducing it. And if you compute this one numerically, it's 0.597. So that means A is the most likely, and C is actually the least likely. That's the answer. And so what happened was that Newton basically did the same calculation and sent it back. This was in the very, very early days of probability. So there are a couple things I find interesting about this, aside from the fact that it's just good practice with writing these things down. First of all, at the time, 1693, if you wanted to solve a problem like this, you had to go to a genius like Isaac Newton. Whereas now, all you have to do is take stat 110. So we've come a long way since 1693. That's nice. The other interesting aspect to this problem is that Newton did the calculation correctly, but he actually gave an intuitive argument which was wrong. Now, I'm not going to take the time to go through his wrong intuitive argument because it's kind of confusing and wrong. But Newton got the intuition wrong. He got the calculation right. And there's an interesting way, if you try to read his intuition, it's very confusing. Okay, I actually read the original a couple years ago, and I was trying to understand what he was saying. It's just kind of this very confusing intuition. I liked the fact that he did the calculation and was trying to provide intuition, but the intuition was very confusing. So at first I couldn't tell, is this intuition correct or incorrect? Okay, and then another statistician, Steve Stigler, had a very beautiful argument showing that Newton's intuition had to be wrong, even if you couldn't understand it. The reason that Stigler gave was that if you look at Newton's argument, whether you understand it or not, nothing in that argument depends on the fact that the dice are fair. So if you change the probabilities for the 6 sides of the dice, Newton's argument would still claim that this one is the most likely, okay? But if you change this you can easily do a similar calculation where the probabilities are not equally likely for the 6 sides of the dice, you can play around with it, and if you want, you can make C the most likely when it's not a fair dice. But Newton's argument would not reflect that, so therefore it couldn't be correct. That is, Newton's argument is invariant if you change the probabilities, but this result is not. So okay. So anyway, even Newton didn't find probably that intuitive, but he was able to do the calculation correctly, and now all of you can do that easily too. All right. So that's just another famous gambling problem. All right. So now the topic for the rest of today and the rest of this week is conditional probability. And I have a lot to say about conditional probability. We're going to use this concept over and over and over again for the whole semester, and hopefully you'll continue to use it even after the class is over. The question that we're trying to address is, we have all these probabilities, okay, but in practice, you sort of like you live each day of your life, and hopefully you learn new things every day, right? Hopefully you learn new things every day. Now, I said on the very first day of class that statistics is the study of uncertainty, right? So unless you're like completely, extremely dogmatic and you're 100% sure of everything, okay? Unless that's the case, you have uncertainty about a lot of things, but you keep learning every day. At least that's what I consider the ideal, right? You kind of have an open mind, you have some beliefs, but you have a lot of uncertainty, you learn new things every day, right? So that's a very, very generic situation. The question is, how should you update your uncertainty and update your probabilities based on new evidence? That's the question. So you can see why that's kind of a central question in science and in philosophy and just in thinking, right? It's just how do you update your beliefs? So how should you update probability / beliefs / uncertainty when you receive new evidence, right? Like if you're doing science and you do an experiment and you learn something, right? If you're investigating a crime, you find clues and things like that. You have to update your uncertainties. Okay, so based on new evidence. And it's generally a sequential process, right? Because you may have some probabilities today, and you learn things later today, and you update your probabilities, and then you'll learn more stuff tomorrow, and you update again, right? So your old probabilities get updated to new ones, but then the new one becomes the old one, and you update that, and you keep updating and updating, hopefully in a coherent, consistent, logical manner. So we're going to develop, the mathematical and statistical ideas of how do you do that. All right, so you can see this is kind of like a very deep, very broad question. And in fact, I like to say that conditioning is the soul of statistics. So possibly that says more about me than it says about conditioning, but that, I don't really know how to quote myself, but anyway, I'm going to quote myself. There. That is a good motivating principle for this course. Everything relates to conditioning in one way or another. All right, so now I've set this up as something very important, and let's kind of say, okay, what's the definition? How do we do math? This sounds a little kind of philosophical. This is like the philosophy of science. Philosophy of science is all based on conditioning. But how do we do math, not philosophy? Well, we want to write down what's the probability of A given B. So this is the notation we use. We have one event given another event. So we pronounce, we just draw a vertical stroke and pronounce that as given. So this is the probability that A occurs given that B occurs, right? So our interpretation is that initially we had some probability P of A for A occurring, okay? Initially, we don't know whether B is going to occur or not, right? Then, suppose that we observe that, B actually did indeed occur, okay? Now, if A and B are independent, then that's going to be irrelevant. But if A and B are not independent, then that's valuable information, and the question is, how do we update our probability for A? Okay? And the definition is that this is just the probability of A and B divided by the probability of B, as long as P of B is greater than 0, since we don't want to divide by 0. So that's a very simple looking definition, right? It's just this over this. It sounds like this very complicated, general, deep, subject, but all it reduces to is just a fraction, this over this. So, and we're going to prove some theorems today. We're going to prove actually many theorems today, but each theorem is so easy that it may not seem like how can this be useful. But then we're going to be seeing examples over and over again for the rest of the semester why this is a useful concept. All right, so just to quickly give you some intuition for this definition, I'll explain this in two ways. I'll call it intuition 1 and intuition 2. Here's intuition 1. Just like, why define it this way? And because we already have some intuition. I already told you the intuition of what this means is the probability of A given B. So if you could say it's a definition, but I want this definition to actually correspond to what we might intuitively think is a reasonable way to do conditioning. So in intuition 1, I call pebble world. And for that, we just need to draw a sample space, S. S is our sample space. Now, we've moved beyond the naive definition of probability. So we no longer assume that all outcomes are equally likely, but let's assume that there are finitely many possible outcomes. Each one is represented by a pebble. So I'm going to explain what this picture means. So just for the sake of example, I drew 9 pebbles. And the constraint on the pebbles is that the total mass equals 1. Each pebble has a certain weight or mass. The assumption is that the total mass is 1. That's not much of an assumption because we could always define the units of mass so that the total is 1. But anyway, we're assuming that we are using units where the total mass is 1. Okay? That's all we have. This is a sample space, so if you were paying attention, we talked about sample spaces. That's all possible outcomes of our experiment. So there are not, in this example, there are 9 possible outcomes, and each one, it might be that they're all 1/9, or they might be different probabilities. That is, some of the pebbles are more massive than others. Okay, that's the setup. Now, we've talked about the correspondence between probabilities. Between events and subsets, right? So an event is just a subset. So for example, let's suppose that this is event B. So I'll just circle these 4 pebbles, right? Because an event is a subset. Therefore, an event is a set of pebbles. Okay? So suppose that's B. And we want to do P of A given B. And think about what does that mean? Well, what that means is, first of all, the interpretation is that we learned that B occurred. Therefore, all the pebbles that are outside of B, that's the other 5 of them, are now irrelevant because they didn't occur. We know that one of these ones occurred. So all we have to do is get rid of pebbles that are not in B. In other words, pebbles in B complement. Anything in B complement is now completely irrelevant. We are restricting to the part of the space that did occur, and we don't care about the part of the space that didn't occur. So we just erase these 5 pebbles, and I could erase them, but then you wouldn't see them anymore. Well, I'll put X's there. You know that they were there, but now they're gone. Okay. Now we just have these 4 pebbles. All right. That's our world, right? We're thinking of the sample space as the universe, but our universe got restricted to B. That's what we're doing. Now this is our new universe, right here. We're just going to do the usual laws of probability, everything the same as before, okay? And if we want the probability of A, maybe A looked like this. If this was A, just for example, 3 of the pebbles in A were outside of B. Those are just irrelevant now. The only part that matters is the part that's A. That's what this is, A intersect B. That's the pebbles. In this example, there was only one, but I could have circled this one too. In this example, there's only one pebble that's in A and B. And we're working with that. The only question is, why do we divide by P of B? And the reason is that it is an obvious technical difficulty. I said, get rid of these pebbles that are not in B, and then just do what we were doing before. The only problem is when we got rid of those, now these ones don't have total mass 1, right? So all we do is renormalize. Renormalize is just a fancy word saying multiply by a constant so that the new mass, total mass, equals 1. And you can check for yourself, just with easy algebra, that this is the correct normalization, that if you divide by P of B, you're going to make the total mass 1 again. The reason is just that if we let A equal B, that's P of B over P of B equals 1. So renormalize to make total mass 1 again. And that's it. That's the end. So this seems like an intuitive thing to do, right? We get rid of the part of the space that was irrelevant and then restrict to that part, and we need it to add up to 1. That's all we're doing. That's what that definition is. Okay. I promised you 2 intuitions. Some people don't like Pebble World. It may seem abstract at first, but I promise you that the more you think about it, the more helpful it will be until you finally feel that it makes sense to you. But it's also helpful to have another intuition. So here's intuition 2. There are different perspectives on what does probability really mean. This is one perspective. Here's another perspective that I call intuition 2. Rather than Pebble world, let's do what I call frequentist world. In Pebble world, we just do the experiment once, and we play around with the pebbles, and we see what is kind of the rational probabilities to use. In frequentist world, we don't just do the experiment once. We repeat the experiment over and over again. I'll just say many times. One philosophical objection to this is how many is many? Is it infinitely many? Is it a million times? And is it really possible? It's like, it gets into all that, is it possible to step into the same river twice? Or, that was that ancient Greek asked that because you've changed it after the first time you step in. So can you do the same experiment over and over again? That's a deep philosophical question, but let's just assume you can. You can do the same experiment over and over again, and here's what we do. Assuming that we can indeed repeat exactly the same experiment over and over again, then one interpretation of probability is long-run frequency. And that's a pretty intuitive, like if you flipped a coin, 1,000 times and 612 of them were heads, then you might say, okay, the probability is about 612 over 1,000. So you're interpreting probability as long-run. In the long run, what fraction of the time does the event occur if you repeat the experiment over and over again? Okay, so now all we need to do is make a list of all the repetitions. So, you do the experiment. I don't actually know, depends what the actual experiment is. What do the results of the experiment look like? Well, let's suppose we're just generating some binary data. I'm just making up some numbers here. I'm just pretending it's binary for some reason. It doesn't actually matter. 0, 0, 1, 0, 0, 1, just whatever, 1, 1, 1, 1. We're repeating over and over again. We're generating lots of data, okay? Now, what we do is circle the repetitions where B occurred. And I haven't defined what B is, but I'm just drawing a picture for illustrative purposes. So suppose that if this was the outcome, then in fact B occurred. This one, B did not occur. This one, B did occur. Okay, and so on. So just repeating many, many times, only select the ones where B occurred. Okay? Now, among those, just the circled ones, what fraction of time did A also occur? So when I say, so that should be a pretty intuitive way to think of it because we're just thinking, well, given that B occurred, then we should restrict our attention to just the circled experiments where B occurred, because we're given that B occurred. Among those, what fraction of the time did A occur? Okay, so if you think about this intuition a little more, you can also see why this corresponds to this. All right, so now let's get some theorems. We only have 5 minutes left, but the theorems are extremely easy, so we're okay. All right, so theorem 1. Suppose that we wanted to find the probability of A and B, okay? How would we go about that? Well, basically I would take this equation, and I want this, so I would multiply both sides by P of B, okay? So that's theorem 1. Probability of A intersect B equals, let's see if I get this right, P of A given B times P of B. I'll write it the other way, P of B times P of A given B, using the commutative property of multiplication. So that's true. We just proved it. Let's actually prove another theorem. Just to save some writing, I'm going to prove it in the same line. We could have instead used P of B given A here, and to do that, just swap the A and the B, right? But A intersect B is the same thing as B intersect A, so I've just swapped the A's and the B's. Now, if we did it that way, we would get P of A times P of B given A. Right? Same thing, I just swapped A and B. Okay? So therefore, we've just derived 2 theorems in less than a minute about how to get the probability of an intersection. Question? Stretching. Okay. Don't worry, we only have 5 minutes left. Then you can take a nap. Okay, so that's good. Notice, by the way, that if A and B are independent, remember the definition of independent from earlier today? That would have just said here P of B times P of A. So independent is the case where P of A given B is P of A. That says intuitively, that says conditioning on B does nothing. All right, well, we're on a roll here, so let's do some more theorems. Theorem 2. Let me just generalize this to n of them. A1 through an. So I want to know what's the probability that all of these events occur. Well, just applying this multiple times, right? Formally, you can use induction, but I'm just using this repeatedly. We're just going to get P of A1, and then we're going to do P of A2 given A1, and then we're going to do P of A3 given A1 and A2. And we're going to keep going like that. An given all the previous ones, right? And actually, this is not just one theorem, but n factorial theorems. So we're extremely efficient today. It's n factorial because I could have started with A7 and then done A4 given A7 and kept going like that, right? As long as you're adding a new one each time, conditional on all the previous ones. So hopefully you all see the pattern here, the n factorial ways to do it. And for some, I mean, I'm kidding about the n factorial, but I'm not. I mean, first of all, it's true. And secondly, for some problems, if you try to do it in one order, it's going to be really hard, and you try a different permutation, it'll be really easy. So it is useful to think about these different orderings. Now, last theorem for today, theorem 3. I would like to relate P of A given B to P of B given A. So I'm going to go back up here, and I'm going to say, let's see, I want P of A given B in terms of P of B given A. So I'm going to divide both sides by P of B, okay? P of A given B equals P of B given A, P of A over P of B. I just proved it. I just divided both sides by P of B. End of proof. This theorem is called Bayes' rule, and it was discovered in 1760-something by Bayes, who was a Presbyterian minister who was doing probability on the side. So the proof is completely obvious. I just divided by P of B. The implications are extremely deep. There's a whole field of statistics, Bayesian statistics. It has controversies have raged for centuries just about this kind of thing. As I wrote it here, it's uncontroversial, but the question of how to use it and how to think about it, it's very deep. So this is like one of the most useful theorems you'll ever see, and yet it's just easy algebra. All right, so that's all for today. See you on Wednesday.